My name is Ryan. I'm a process engineer. I work for DHI Water Environment, Inc. DHI, and it was originally Danish Hydraulic Institute, so it's a hydraulic modeling company for the most part. It's no longer technically an institute, so now I think we're just DHI. But yes, we are on a quest to help solve the world's toughest challenges in water environments. That's why I joined the business. I joined this company actually. Yeah, there's teams that work in mines and groundwater modeling, oceans and coastline and like wave tidal analysis. Cities, of course, which is what we're talking about today, and then there's a river modeling team, and yeah, pretty much every time I talk to somebody in DHI, they're working on some new water environment that I've never even heard of and didn't know it was an issue. But as we are a hydraulic modeling firm for the most part, there's a whole suite of software that we use. I guess some of it is like the gold standard for hydraulic modeling, and what we're looking at today is our tools for wastewater treatment modeling, so that's West, and Mike Urban, which is a hydraulic modeling, a 2D modeling platform for collection systems. And we've got DIMScore here as well that we'll talk about kind of towards the end. I think that's enough about DHI. You guys probably want to see something about the project. Peter, if you want to say a couple words about Aarhus or Denmark and where it is.
Yeah, well, Denmark is, compared to US, is a quite small place. We are just 5.6 million or something like that. And the area where we go into here is Aarhus, the second largest city. And we are just around 350,000 people, so it's not that much. Here we are landed in Viby, and what you're looking at here is the wastewater treatment plant that we are going to talk about. And it is activated sludge plant with pre-sedimentation, and it has activated sludge secondary treatment, a tertiary treatment as a filter. Could you?
Yeah, there we go.
Okay. So we are in Viby, and I'll try to step into the shoes of Aarhus Water because they had a problem. And the problem is that they want to extend the plant from 90,000 to 120,000 person equivalent. And doing that is not so easy because they have other plans actually. They would like to build a new big wastewater treatment plant at the harbor side, and therefore building a new extension is something they are not very keen about. So they were thinking about something like this. How can we actually increase the load of Viby wastewater treatment plant in just a period of 10 years or something like that, because then the new wastewater treatment plant will be working and we don't need it anymore. Usually, if we want to extend the plant, it is something that will last for many years. Many plants have maybe 70 years of lifetime expectancy, but in this case, the extension will just be for a very short while, less than 10 years. So, how can we do that with tight nitrogen and phosphate limits and do that at a low cost? Because we are not interested in investing in a lot of buildings. So can it be done for a very short amount of money, just $2 million for a 33% extension? And the first thought they had is, we think it's possible. We want to make a tender to see who can actually deliver this for us. So that is actually the problem that we are trying to solve in this project.
And just for reference, Peter, correct me if I'm wrong, the ammonia limit for discharge is 2 milligrams per liter, total nitrogen of 8, and total phosphorus 0.4 milligrams per liter.
Yeah, you're right. Yeah, so it's quite tight. Okay. Limits.
And that's pretty standard in Denmark, I guess, but still, it's not something.
The total P is lower than that. Yeah. So but it is also about finding the right consortium to fix that. And actually, the company called Techglass, you see there to the right, is actually the main company in this situation, delivering and having the contract, if it is possible to achieve this contract, which we won actually, but they are the contractor. And Techglass is a company that is specialized in delivering machine projects mainly. That could be dewatering of sludge, can be filtering, pre-filtering of wastewater instead of primary tanks, sedimentation, or it could be effluent filtration and similar things. And they are quite good at that, and also delivering on time and budget. So, and furthermore, they are very good at having a close collaboration with customers. So it's a quite effective company. They could not do this themselves, and therefore you can see all the other names around it. You can, I had to start with Niras, the company at the bottom. That is a big consulting engineering firm that is doing, how to say, turning all the ideas into drawings and eventually tenders that can be used for building the whole thing. DHI is, well, the company that comes up with the ideas about, in this case, how the process can actually be turned around in this plant so that we can achieve the increased load. And the S-Select is a company that is going to help us to deliver some more, you can say, densified sludge that settles a little bit better, which is something that we would like to include in this project since there's a lot of hydraulic load on it. Maybe I also have to say a few words about Aarhus Water, the customer. And of course, they are the one who's paying us for this, but it's also an interesting company in many ways. It is very innovative, and just, how to say, coming up with a question as we have here is actually a way of thinking in that company. They want to be innovative, try to find new ways to do things. And they are having a new strategy right now that also shows that they are a bit different, because usually we just focus in such a company for delivering water and treating wastewater, but their main focus is actually now health. So they are focusing a lot of things around health. I think maybe they have something new there and something important that will make them move in a new direction in the future. So it's a very innovative company. This is an overview of the plant, and if you go to the right, you can see digesters. Just a little bit left from the digesters, you can see sedimentation tank, and in the blue area is actually where we would like to do some changes, and that is the activated sludge plant. That is the part that we need to increase the capacity of. So what we have right now is to the right, that is rectangular tanks, and that the first one we see there with the yellow marks there is one plug flow tank where we or raceway, sorry, it's a raceway tank where they perform side stream hydrolysis, and that is for their biological phosphorus removal. The water, primary effluent, goes into the next tank combined with the effluent from the side stream, and then you have 4 denitrification tanks. And the denitrification tanks are getting water from mixed liquor from the following tanks to the left.
The next screen with the nitrification tanks, we can see nitrification tank 1, 2, and 3. There's a potential to step feed between the two and the nitrate recycle back to denit tank 1.
And we have the effluent there from tank 3 that goes to the many clarifiers. Some of them you can see at the back. So that is the setup right now, and we have to do something different to get the capacity of this plant to treat 120,000 instead of 90,000. So if we take the next one.
Yeah, the next one I kind of talk a little bit about our process, our workflow for a project like this, and we've been doing a lot of these, especially, you know, I've got the chance to work with Peter, who's an absolute expert on this. He can take one look at a plant and come up with 10 ideas immediately, and it's so much fun to work with him. He's like a hype man when you get him into a wastewater plant. It's perfect. But yeah, we start with a plant process review, where, oh man, lost my notes. Where, yeah, we spend a lot of time on site usually and working with the operators, you know, trying to see how is the plant actually operated, what kind of bottlenecks are there, you know, can you get flow from tank A to tank B, and if you do, are you able to aerate it a certain amount, and yeah, really what are the capabilities and what are the bottlenecks, what are the targets, what kind of projects have been done, right, because these things usually don't run exactly as they were designed 50 years ago, because there's been a lot of projects between now and then. Yeah, so we would, like most consultants, will take some time to evaluate the historical data set and try to find out kind of what the loadings have been and how the plant's reacted to those loadings and how it's been operating. And then in this case, we kind of went straight to process design. Sometimes it's flipped. Sometimes we do modeling first, but I would say, yeah, Peter kind of went to town, went to the drawing board, and started coming up with some systems. You know, how can we rearrange or rethink how we run that activated sludge system, and, you know, do we have the volume for nitrification in the winter, and, you know, how much space do we then have for denitrification, and how much carbon is available. And then we take those ideas and put them into our process simulators. So we use West, and at this time we'll start to build in controllers, advanced controllers that kind of stack on top of one another and try to figure out what's the best way to actually operate or actually control a process like this. And by doing that on smaller and smaller time steps, we can get higher resolution in our control and then actually squeeze more capacity out of a plant in that way. And at the same time, evaluate what's the capital expenditure that would be required to implement something like this. So you can test, do you need more volume? If you do, you can put in another tank and kind of evaluate whether or not, you know, what's the benefit of adding that tank compared to what's the cost of adding it. You know, can you just add a pump? Can we add some diffusers or something instead? So it kind of becomes an evaluation of the CapEx required to implement something. And that's in partnership.
Can I just put into,
in this case, Aarhus then? Yeah, go ahead.
I would just say this is actually a prime place to go in, because here the consortium has to find out, is it actually possible to do the project for 2 million? So that is an essential place to evaluate that the consortium had to go into. So now the consulting engineer, together with TechLabs and so forth, evaluated, okay, we think it's possible to deliver something like this for 2 million.
Yeah, and at that time, the engineer and whoever would go ahead and install any new equipment that's required, if there's a new sensor or new diffusers, baffle walls, stuff like that. And then we use our DIMS core software to control that new system and implement the controls that we tested in West. And then the final step here is kind of taking advantage of the DIMS data management software, and you can set things up like automated reporting and try to automate some monitoring workflows that maybe already exist in our manual operation. But yeah, so that's kind of our cycle that we followed for this project, and what we'll focus on a little bit is the West modeling that was done here. So I took a screenshot of a video of me running the model and giving us a little bit of a tour of West, a super fast one. So this is our baseline layout, and you guys are just seeing the West layout or the graphical user interface. This is kind of how the plant looks that we're testing. You can add new blocks, and maybe you want to test what do I have here? Membrane moving bed bioreactor, an IFAS system, sand filter, secondary clarifier, connect them with these like hydraulic and model connectors. So you select what's the outlet stream, what's the inlet stream for the next one. And then for each model block, you can select the actual type of model to be used. And for this particular settler, I've selected the Tachys model set, but there's a handful in there that you could choose from. Yeah, one of the main advantages is this controller that you can use. This one's a PID, but there's a handful of controllers, and you can connect them really in any way you like. And then you can open this help window if you need it and find out something about how to set up or tune the controller, what the different parameters mean. But the main thing I wanted to show is that you can open the model editor here, which we've done, I think, for this project in particular. So I have a custom model library now. And you can modify the base components of these models. So you can look into the Goyer matrix and change. And none of these things are locked for editing, is what I'm trying to show. So you can play around with the different kinetic expressions or constants, and then look into the model. This one's an anaerobic digester if you needed to see how it worked, or if you wanted to change some aspect of, say, last year we were working on the pH balance in one of those for a while. So yeah, it's completely open. You can go in there, you can open the controller module, for example, and customize how the controller will interact with the model, or the activated sludge models. Here's just an example of making an influent file. Maybe you wanted to add H2S, VSS, or ammonia data. You can do that in here and fractionate those influent data into stoichiometrically significant figures for West to use. So that's the tour. Now, oh yeah, one more aspect of the tour. You can run some of these advanced experiments, including Monte Carlo uncertainty analysis, and get a better idea of how uncertainty affects the model, which is pretty critical in any modeling activity. So now we're running. I just started the model, so right now it's set at 90,000 people equivalent, and these are some dashboards that we set up so we can see how our model's running, and I guess in real time is the word, but and we also added this widget where we can change the flow from 90,000 people to 120,000 people equivalents. We're talking people equivalents mostly because there's a big industry associated with this plant. So we end up with a lot of BOD and nitrogen coming from that industry when it's being introduced. So I think it's just from running the baseline model, we were seeing that it's pretty unlikely that the plant could handle that total nitrogen load. So what we did is added this control system where I can hit this button and push a new parameter set in and unlock this control set that Peter and our expert modeler Enrico built, and run the same influent file. So right now we're running with 90,000, and once we get up to day 7 or so, we'll do the same thing where we bump the flow up by 33% right here, and you can see the before and after effects on each of these charts. Yeah, and just from running the same setup but adding some online control system. I mean, they already had some online control, but this is we'll talk more about the controller in a bit, but we can see that there is some space to improve the operation. You can also see here that we didn't quite reach a steady state, so in practice you would run probably a steady state simulation in between. As we continue towards steady state, we're actually getting more nitrification, which looks good. But yeah, the main idea was that we were able to get better treatment in that same system in a virtual, modeling environment, but with increasing the resolution and the amount of changes that we're able to make. Does it make sense, Peter? Anything to add?
No, what I think is important now is to show that the different layouts that we are trying. The first, you said that there's some more controllers, but what we also did was to add some more aeration, and I think you're going to show that later on. But as you probably remember, we had a lot of DN tanks to the right, and we are actually turning some of these DM tanks back to some, or back, we are turning them into aeration tanks, and by that actually increasing the aerobic volume that is needed for nitrification, especially in the winter time. So that is also what we did in this case. But I guess you will just,
and
that is just...
Yeah, we'll get there. One other thing that I wanted to show is that we tested the difference here between keeping that first tank as side stream hydrolysis and activating some BioP versus taking that tank and just adding it to the nitrification, denitrification, specifically denite capacity for the plant. And what we found was the chemical cost for chemical precipitation was super low. So it actually, like the cost difference between, the chemical cost difference between running BioP and running, with this extra denitrification volume was like, I think, I can't even remember if there was a difference or which one was higher. I mean, it was super minimal, and that's because we're dosing methanol either way to support denitrification. So the chemical precipitation was really low, and I think they're using, Peter, is it ferric?
Yeah.
Yeah, the ferric dosing rate was low enough that the cost difference between the two was pretty low. But what we ended up with was significantly better total nitrogen control when we ran with full nitrification, denitrification in that tank. And then we were better able to control, at least virtually, these, better able to control aeration and ammonia peaks as peak loads come into the plant. It was a lot easier to control the effect that has on effluent. So we combined all these things into a full solution for the plant.
The first thing was actually, by also doing all this simulation, we could see that we definitely needed some more aerated volume. And that was to ensure that we could have nitrification during, especially during the winter time with low temperature. We have temperatures down to 10 degrees in Viby at the winter time, but also to take peaks of ammonia coming in. So I think if you continue.
Nice. Yeah, well, as you said, we started out by the realization that we needed more oxic or more aerated volume. And to do that, we knew we would need more aeration capacity. So Peter and the team designed some process air blowers, or a modification to the air blowers that exist, and actually added some, or modified the diffuser grids at the plant so that they can better control aeration in different zones. We'll show you what that looks like. And we're also going to need to increase the denitrification rate, or find a way to optimize it. And that's also done here with, or not also, but that's done with our advanced DN or NDN controller.
Yeah, the reason for that is that we actually now removed some of the denitrification volume because we introduced aeration. So everything is not, or the denitrification with normal wastewater isn't sufficient. We need to increase the rate, and therefore we add some external carbon with a higher denitrification rate.
Exactly, and you guys also included this load-based control selector. So there's multiple control modes, and those are automatically selected based on incoming the TKN load. And there's also a return sludge controller that was already actually part of this plant. So then there's ammonia-based aeration control as part of the solution, and then there's also this nitrate controller, which is also, all of these cascade to a carbon dosing control mechanism. And again, we'll show you some curves, and we'll look at how that actually works in practice. And the last part of the project was during peak flows. There will be some, or we're right on the cusp of straining the secondary clarifiers. So to provide a little bit of safety in that process, we looked into the granular activated sludge, or maybe we should call it densified activated sludge. We didn't quite make granules here, but don't probably need them. Installed some hydrocyclones and ended up with significantly higher SVI and settling velocity. So it's an increase in clarifier capacity without adding clarifiers.
Yeah, that is also because we have to increase the sludge concentration of the activated sludge. And when you do that, the settling velocity go down if you have more sludge. And therefore the hydrocyclones system there can help us to ensure that we can settle all this sludge.
Exactly.
And just a little comment from my side. Lego is pretty squared and one fits all, but I think it's important to say that it's a customized solution that you build to the wastewater plant. So it's customized to the concrete that that's on the plant and what the sort of problems that the plant is facing. Is that correct?
Yeah, exactly. These Legos
exactly.
are put together pretty specifically for this solution, and yeah, there will be rearranged for every plant. It's not a one size fits all, and the Danes really do love Legos. They're a proud race, and it's a Danish company, and they just have Legos everywhere if you ever go visit. Okay, Peter.
Yeah. So now
I release you. Introduce the solution.
Yeah.
Yeah, this is before.
Yeah. So now we if you just continue. Before we had to the right, we have the side stream hydrolysis tank. It is now turned into a denitrification tank. So the primary effluent go over there, and then the tank 3, 4, and 5 there in yellow is actually now not denitrification tanks, but MDN tanks, meaning that we can turn on and off aeration if we need it due to ammonia peaks or because the temperature is lowered, so we need more oxic volume. And the flow from those tanks goes still into the tanks you see the raceway to the left. And 1 and 2 is strictly nitrification, but now tank 3 to the left is actually turning into a post-denitrification tank. Before it was also doing some denitrification, but now we are adding the carbon for denitrification to this tank to increase the denitrification rate and to remove the nitrate so that we can comply with the total nitrogen. And still in that tank, we have the possibility of aerating if the ammonia is getting too high. So the main process in tank 3 is now post-denitrification, and before it was nitrification. So this is a new setup.
That's before,
in the end tanks.
And that's after.
Yeah.
You notice there's also a blower building.
Yes, because the 3 tank, 3, 4, and 5 need some air, and they are getting that from a small building, and that is the only building being made actually in this case.
Yeah, so that was probably the primary construction cost. Was building a small shed. And
and then
blowers
except for that, it's machine. Yeah. There's a need of controllers to do this. As you remember, all the different Lego blocks there, they need to be controlled. And ammonia is one of the things we really need to look for. And if the ammonia coming at the plant is high, then we need to start aeration, because or else we cannot keep the ammonia peak down in the effluent. And in the post-denitrification tank, we need to look for nitrate, and if the nitrate is getting too high, we start dosing and increasing the denitrification rate. Then we have the recycling of sludge from to the DN tank, and that is also controlled. And furthermore, there is a return sludge control that is flux-based, which is something that is already implemented at the plant. So there's a lot of controllers.
So it's maybe simple to control any of these one aspects of a plant. You know, it's a PID feedback control loop maybe, but when you're controlling all of them at the same time, you can see in the background here is a screenshot of what the tuning or is it tuning, or are they set points, Peter? I can't tell. It's all in Danish.
It's both. Yeah.
Yeah.
And one
so there's a lot of
things
to control.
Yeah. What I would like to say here, that is actually how to say, Aarhus Water themselves doing this because they're very good at automation, and the DIMS core is something they use for making their controllers. So they're very capable of doing something like this. So it's also, you can say, collaboration of what we would like to see from the model and what they actually implemented. I think we can step forward. This is just how it looks.
Screenshot of the operator's layout.
Yeah. So in a way, it's not so important, but it is possible here to press a button, click on different things, and you get curves up, and you can see here all the different values, ammonia, nitrate, whatever, different places at the plant. But all these, there's a lot of sensors involved in this, and they are used for the different controllers needed. And I think that is the main message from this one. I don't know how many sensors is involved, but a lot. This is just a case, shows the load calculated in DIMS core that gives a load of ammonia coming in. And if you see the blue, light blue one at the top, it is actually when the load of ammonia is getting too high, then we know that we cannot, how to say, limit ammonia peak if we don't aerate in the DN tanks, the NDN tanks. So now we turned on the NDN tanks, former denitrification tanks, when this peak come in. And that is the main measures here. There's a lot of different subparts of ammonia loads, and it's just possible to show that in items like this and use them for controllers.
Yeah, I can unpack that a little bit. We're looking at the ammonia loads from all different parts of the plant. So that includes, return from the, what do we have here? A decanting process. There's the demin, which is an anammox process that's recycling to the front end of the plant, and then of course some influent ammonia. And that threshold that we put in right there at 800 grams per minute is the loading threshold that will trigger aeration in the first swing zone. And there's higher thresholds, I think 900 and 1,000 for that trigger aeration in the other swing zones as well.
Exactly.
Okay, and then I've just got a few slides here that show how the controller works, or show the controller working. This is nitrate in that final denitrification tank, the post-denitrification tank. You can see it's off spec at one point here. There's really high nitrate, and if we overlay, or if we show the ammonia curve in the same process tank at the same time, we're getting above 3, and there's a trigger at some point to go ahead and start aerating that tank. This is DO, and at the same time you see the right there above 3.9, the DO spikes up to 0.8, and I think the threshold is like 0.3 or something. And once you hit 0.3, there's a slightly different y-axis, so the time frame's a little bit different. But nitrate's in red at the top. Whenever nitrate is above this pink flat line in the middle, 3, in that tank, we want to be dosing carbon to help supplement the denitrification capacity of that tank. But there's one instance here where you see the bottom blue line, that's DO, measured DO in that same tank. Once DO gets above like 0.3, or actually maybe it's just an aeration trigger, the carbon dosing will kick off. And that's to make sure that we're not just taking up the carbon that's being dosed through like heterotrophic carbon oxidation. It would just be wasted. It wouldn't be used for denitrification. It would just be taken up. So that's one other aspect of the controller, where it'll actually kick off the dosing if you're below 3 and also 3 milligrams per liter nitrate, and also if you're aerating in that tank. So, Peter, the results?
Yeah, maybe it's
2019
part
and 2020.
of the the curve above is actually in 2019, and you can see probably that the MGT there is around 5.7 as an average, and now in 2020 we have up to 13.7 mg because it has been raining a lot. We have a lot of water coming in, and even though that we have this very high load of water in 2020, we are still complying with all values for nitrate or nitrogen and phosphorus and BOD at the plant. So one thing we can see after we change is that there is a more control of the effluent, and we don't see ammonia peak bleeding through. That is important. Again, also, if you look at the nitrate, I think it's probably too much to go into all these details about the nitrate, but what is important here?
I think the dark one in the middle on top, actually, the dark line is effluent, or not effluent, but tank 3.
Yeah, going out, and if you look at the very dark color,
obviously there's more flow in the same period, and the nitrate is actually, effluent nitrate is actually lower, and effluent ammonia is either lower or comparable.
No, the lower one is 19, so it's lower. Yeah, even though there's a lot more flow, we can still have a lower ammonia. So both nitrate and ammonia is lower. Yes, I think we can then go to the settling of the sludge.
Maybe while you are Peter, maybe while you're moving to the next slide, I can see there's a lot of question about size of the plant and MGD and loading and stuff like that. Is that important for this model? Can you fit it into any plant?
Yeah, it's not essential to. It can actually be used for 1 mgd or 30 or 100 mgd. It's not necessary to have a specific size of this. All equations and so forth can be calculated for whatever volume needed and flow needed. But you can see at least here we have a peak load about 30 mgd. This is settling, and the hydrocyclones, as we talked about, should have the ability to make the sludge settle a little bit better. And if you look to the right, you have a hydrocyclone system where the sludge settle in the column there. It's called BB2 to the right there, is have a significant higher clear water than the column, water column to the left. And that indicates that the sludge settling better. At least in this picture. But what did we see in the actual situation? We can see on the next slide. This is 2 curves. The lower one is showing, existing system before we changed the whole operation, not only the hydrocyclone, but everything, aeration and so forth. And you can see that the settling velocity is significantly lower than the red one. So we achieved a significantly improvement in the settling by introducing the hydrocyclones and the overall project. So we are in the right direction. We wanted to have more safety in the settling, in the clarifiers, and it was achieved also.
And we have hidden the axes because this is data that's owned by the plant and the other teammates right now, but. Yeah, we did see an uptick in denitrification rate, and I know this was one of the questions. And we did expect to see better denitrification rate, and our theory at least is due to the targeted carbon dosing, we're able to concentrate the population of denitrifiers and retain that population throughout the diurnal patterns in the day without having to kind of rebuild that as nitrate is made available. But we didn't see the same effect with nitrification. That there was yeah, Peter, maybe you can unpack this.
Yeah, there's no change, there's no increase in nitrification rate, but we saw it for the denitrification probably because of the addition of the carbon making the population of denitrifiers increase. Yeah.
I guess we didn't necessarily expect any, but it's something to track whenever you're kind of trying to densify sludge. Just a quick word on DIMSCORE, I guess. You can connect directly to SCADA, so this thing can operate sort of in parallel to SCADA, and the operator always has the ability to shut it down and revert back to either DO control or some kind of fallback control, and that'll also automatically happen if any connection is lost, or the control system validates data as it comes in and decides whether or not to use it for control. If we don't like it, it'll also shut down the controller, flag that data point, and then we can look into the sensor. Just an example of an automated report. And yeah, I mean, this is kind of the first stage of a digital twin. What you can do is take these data that are being pulled into DIMS and used for control, and also export those to a West model and run that model in an online environment, and ultimately use that to output control that points back to the plant, or maybe to select a control mode, or just to send some recommendations back to the plant, and then the operators get the chance to review it, or use it to calibrate sensor data. I guess there's kind of a slew of things that we can do with an online model, but this is something that DHI has been working on quite a lot. Actually, built one in China and one in Denmark, and yeah, we'll be excited to kind of bring this to market in the States. And yeah,
so
last thing is yeah, go ahead.
No, what I think is important, we can do a lot of things, but I think what is really important is that the question that Aarhus Water had, is it possible really to build this plant extension for a very low amount of money, probably 1/10 of what is necessary? And it was actually possible to do. And we had to go through a lot of details to do this, as we try to show you. And maybe it's a very big mouthful to show here. But anyway, it is something that can be evaluated on many plants. And it is not the only plant that we have found these possibilities of actually making an extension to significantly reduce cost. We have done it in Portugal also, and then we have also looked at it in the US as a peer review of projects. So it is not a one-off that is possible to actually make something cheaper, like we've shown here. As I said, probably 1/10 of what a normal extension should have costed.
No, I just want to say thank you to all the attendants. Yeah, so just thank you to all of you. That's all from here.
Thank you all very much for listening. Enjoy the rest of your day.
Thank you.
Thank you,
Have a good day, guys.
Bye.